So my name is Gray, and I'm from Open Robotics, and I'll be talking about some of the work we've done in the Robotics Middleware Framework project. In particular, how do we get heterogeneous robot fleets to cooperate? Next, please. So first, let's talk about what do we mean by heterogeneous. Next. So different robots tend to be good at different tasks, and there isn't generally one robot platform that can do everything you might need in a complex facility. Next. So maybe you need a robot that can pick up your trash. Next. Or if you're in a hospital, you need trash pickup, but you also need a robot that can assist your patients. Next. And if you're a space hospital, you might need a robot that can repair your spaceship ambulances, right? So if you're a space hospital, you might need all three of these robots in your facility, and they need to be able to work together. Next. But there's going to be a problem if these robots are all made by different vendors, right? So they're all made by different companies that made them in different ways and gave them all different APIs. And so, next. So if you want these two robots to talk to each other, next. Next. Their APIs, you can think of them as puzzle pieces, and if they're not made to fit into each other, then they cannot communicate. Next. And this is a problem if they need to cooperate with each other, because hallways might be crowded, so they might get in each other's way. Next. Also, lifts are difficult to share, and lifts are a precious resource, because if your robots can't share lifts with each other, then you have a fixed limit on how many different fleets you can bring into your facility. If each robot fleet needs its own set of lifts, then at a certain point, you're just going to run out of lifts that you can give to the robots, and then you can't buy any more fleets. Next. So what we do to address this problem is we have a robot traffic scheduling system. So let's suppose Wally and Baymax each need to get somewhere, but they will get in each other's way if they try to go to their destinations. Next. So what we do to make them cooperate is first Wally plans its path and submits that to a centralized robot traffic system. Next. And then Baymax will be able to see Wally's scheduled path, because Wally is also connected to the schedule, and plan around it. So Baymax will know that it can move down the corridor, but it has to stop at that intersection until Wally is out of the way. Okay, next. But this doesn't really address a number of very serious, very real problems that can happen, like race conditions or prediction errors. If a robot doesn't predict how it's going to move perfectly, then you could end up with permanent deadlocks. If the robots, where the robots just can't plan around each other anymore. Next. So we deal with this situation with what we call a negotiation system. So this is the other side of the coin. On one side of the coin is the scheduling system, and then on the other is the negotiation system. So here we have a situation where Wally needs Baymax to move out of the way. There's no valid path that Wally can plan around Baymax. So, so both will try to schedule the plans that they want to have, but the schedule will recognize that there's a conflict between these plans. And this triggers a schedule conflict, which tells the two robots that they need to negotiate with each other. Okay, next. So Wally and Baymax are now asked to negotiate. Next. And the first step is that each of them proposes what its ideal plan would be while ignoring the very existence of the other plan. And then they transmit these plans to each other. So Baymax sees Wally's plan and Wally sees Baymax's plan. And then each robot tries to respond to the other robot's plan with an accommodating proposal. like Baymax at the top right, proposed a plan that like has Baymax move over to the right and then wait for WALL-E to move past and then go to the left and down. Or if it's impossible for the robot to accommodate the other, so like WALL-E cannot move out of the way of Baymax if Baymax is going to follow its ideal path. So WALL-E will reject Baymax's proposal. Okay, next. When WALL-E rejects Baymax's proposal, Baymax hears about it. Okay, next. And then WALL-E will also provide a few different paths that WALL-E can follow, ignoring the existence of Baymax. Okay, next. And then given that information about the different paths that WALL-E could follow, Baymax proposes a plan for itself that accommodates at least one of those possible WALL-E paths. Next. So that becomes Baymax's new proposal, which then WALL-E hears about, and then WALL-E will propose WALL-E's best plan to accommodate Baymax's plan. So now we have two alternate realities, which are basically two different sets of plans for each robot that they could feasibly follow. And then a third-party judge will choose the best one, the best conclusion, the best alternate reality, you could say, based on some criteria which is configurable, but usually the criteria is going to be whichever gets everyone to their destinations in the least amount of time. And you could weigh the different times based on the priorities of the robot's tasks, or really it's up to the system integrator to decide what the criteria should be. Okay, next. The negotiation system can also scale up to more robots. Next. So if we have a three-way conflict between WALL-E, Baymax, and R2-D2, where they all have to get out of each other's way, then we start the negotiation by having each one propose their ideal plan. Next. Every robot hears about every other robot's ideal plan, and then every robot responds to each of the other robots, and it's sort of combinatorial until we end up, in this case, with 6 different alternate realities to choose from, where each robot is accommodating every other robot. And so we have six different alternate realities, any one of which is a feasible plan, but they may have different qualities. Like they might allow the robots to arrive sooner or later. Okay, next. And so our third-party judge comes in again and assigns some kind of cost to each one of these alternate realities, which again can be configured by a system integrator, but usually it's going to be something like how much delay does this option produce overall. And then the alternate reality with the lowest cost is the one that gets chosen. Okay, next. So now, how do we actually perform the integration for this? Next. So negotiating is difficult. This is kind of a novel system, and so most existing fleets that are out there in the world don't know how to do this. They just haven't been programmed for it. So we provide APIs for you. So there's the protocol that I described, and then there's a different puzzle piece for each API that we provide out of the box. So for the full control API, next, that API is meant for fleets that can accept detailed plan commands. So these are fleets where you can command a robot to go anywhere in any way that it knows how to. And so this is sort of the gold standard API, because this allows robots to completely get rerouted around traffic jams and always take the most efficient route possible while taking the traffic of the other robots into account. Next. Then the traffic light API is perhaps going to be more commonly used. this is for fleets that can tell you what path the robot will take, and that can support pause and resume commands. So most fleets out there for mobile robots, they tend to insist on routing the robots themselves. So we can't command them to take a specific path, but we often can tell them to pause and resume what it is they're doing. So this API is meant for those platforms. And what this allows us to do is in the scheduling and negotiation systems, we can plan out pauses and resumes that avoid deadlocks with other robots. Next. And then the third API is for robots that will not accept any commands at all, but they will at least tell us where they are. And this is not an ideal kind of system to integrate, but at the very least, we can, the other two types of fleets can plan around this type of fleet. So it's better than absolutely no integration. Okay, next. So what you do is you have these three different fleets and these three different APIs, and they still don't fit together because none of these APIs knew about each other when they were being made. So next. So as a system integrator, your job is to just create this middle puzzle piece that ties together the fleet API with whichever RMF API is the most appropriate for your system. Next. On top of this traffic scheduling and negotiation system, we also are trying to standardize various interfaces that can be shared across different fleets. And this helps a lot. Next. So this helps a lot with integration and scaling because it all becomes less expensive if the dashboard that lets you monitor your trash bot is the same dashboard that can monitor all your other robots. Then you can have like one set of human operators supervising all of that instead of needing to hire specialists for every single fleet. It also helps with integrating into facilities. So instead of every robot needing to have its own custom integration into the lift, they can all just share the same lift integration by just connecting to the RMF API. And so introducing new platforms into an existing deployment over time becomes a lot more feasible. And this is important. This is very important for consumers because it's kind of dangerous to get locked in to one single vendor. If someday you need a new robot solution for a new problem that you're having, and that vendor doesn't provide that solution, you might need to bring in new system integrators for those new platforms. And that might not be feasible without this kind of standardization. It can also be good for system integrators if you want to enter into new facilities that would be locked in otherwise by a different vendor. So it improves competitiveness, which we like to think is good for everyone. Okay, next. So I'll be happy to take questions at this time.
Thank you, Dr. Gray. We'll now move on to a short Q&A session. Participants, you may submit your questions over Slido by scanning the QR code on your screen. All right, there is one question on the screen now to Dr. Gray. The question is, this communication system is already available?
That's right. So everything I presented is already available. The protocol is ready. There are implementations for it. There are integration tools available. The APIs are still being iterated on, but they are tested and working. And we have continuous improvement going on, but it's definitely ready to be tried out. Will there always be a solution from the traffic negotiation? So that is situational. So for example, an obvious case where there won't be a solution is if let's say you have two read-only fleets that conflict with each other, then obviously they can't, they can't solve, they can't get around each other because they're just going to both be very stubborn. If you have a read-only and a traffic light fleet, there may also be some risk of permanent deadlock depending on how risky you want your system to be. So, read-only, it could cause problems, potentially. Read-only and a full control should never get permanently deadlocked. In fact, anything versus full control should never get deadlocked. Traffic light versus traffic light, that is also somewhat situational. If you deploy your system in a way that the traffic light robots always start and end in places where there's guaranteed to not be conflict, then we can guarantee that there will be no permanent deadlocks. But if you have your traffic light robots start and end in places where there may be conflicts, then there is a risk of permanent deadlock. So it's somewhat situational. I would say if you integrate your system well, then you can mitigate all of those risks. Okay, let's say I'm a robot vendor and I am selling my robot for some marketplace which already has other robots. How to go ahead with traffic negotiation then? So let's see. So this really depends on the consumer at the end of the day. If the consumer of the robots, meaning the facility where the deployment is happening, if that facility has already adopted RMF, then all you have to do is make your robots RMF compatible. If they have not done that yet, then you would have to convince the facility managers to get their existing vendors to buy into RMF.
Yep. Thank you, Dr. Gray.